Hello students, in this session we are going to find whether we can define an exponential function in complex analysis with the same properties which we see in a real exponential function. When we were dealing with the power series, we had defined that e raised to z or exp of z is equal to summation n is equal to 0 to infinity set raised to n divided by n factorial. So, it is of the form of a power series, usual power series, which is of the form summation n is equal to 0 to infinity a n into set minus a the whole raised to n. This is the general form of the power series we had dealt with earlier. So, in case of our exponential function, the a n here will be 1 by n factorial and the a will be 0 here. Okay. So, now let us see how we can calculate the radius of convergence of a power series. So, let us see limit n tends to infinity modulus of a n divided by a n plus 1, which is equal to limit n tends to infinity. Since we have a n here to be 1 by n factorial, a n plus 1 will be 1 by n plus 1 factorial, n plus 1 factorial, and since it is factorial they are always positive. So, no need of the modulus, we can just forget the modulus sign, and that is nothing but limit n tends to infinity n plus 1 factorial divided by n factorial, which is equal to limit n tends to infinity n plus 1 into n factorial divided by n factorial, and both of them cancels out, and what we get is the value will be tending to infinity. That means the value exists. We are not facing a situation where the limit is not existing. Here it exists. So, I can say that the radius of convergence here is infinity. So, please refer our preposition 2.2 which we had already dealt with regarding the radius of convergence. So, since the radius of convergence of the power series of the exponential function is infinity, that means that e raised to z, which is equal to summation n is equal to 0 to infinity z raised to n by n factorial is convergent in the entire complex plane. Okay. Now, suppose I am calling f of z is equal to summation n is equal to 0 to infinity 1 by n factorial into z raised to n, which is nothing but e raised to z. Okay. So, since the function or the series which is the function itself is convergent For a particular r strictly greater than 0, here we are having r is equal to infinity. By preposition (2.5) B part, we are going to get the following. We are getting f of z to be infinitely differentiable in entire complex plane C by preposition 2.5b. Okay. And also we have from the same preposition f dash of z is equal to summation n is equal to 1 to infinity n into 1 by n factorial into z raised to n minus 1. For those of you who are having some doubts whether this is correct or not, I am just stating the preposition. Suppose if f of z is equal to summation n is equal to 0 to infinity a n into z minus a the whole raised to n with radius of convergence capital R strictly greater than 0, if we have something like this, then f k of z, that means the kth derivative of f of z is equal to summation n is equal to k to infinity n into n minus 1 into etc. into n minus k plus 1 into a n into z minus a the whole raised to n minus k. Okay. And this is also convergent, we get that this is also convergent with radius of convergence the same r that of the f of z. So, this is the preposition 2.5b. Okay, we are using this, and here we are having instead of k we are having 1 because it is f dash. Okay, let us continue, and that is equal to f dash is equal to summation n is equal to 1 to infinity. The n and n will cancel out and you are going to get 1 by n minus 1 factorial into z raised to n minus 1, right. That is equal to just rewrite, I can write like this. See. So, everywhere we are having n minus 1. So, instead of n minus 1 I am changing it into the variable n. And what we are now getting is this is nothing but a function f of z. What was our f of z? F of z was our e raised to z, right. So, what we now got is d by dz of e power z, which we defined is nothing but e power z. This is something which we got now. Which is very important, and you can understand that this is very similar to d by dx of e raised to x, which is equal to e raised to x in real sense. When we are thinking about in real analysis, the exponential function is having the same property. Okay. Now, our next claim is e raised to a into e raised to b is equal to e raised to a plus b for every a comma b that belongs to the set of all complex numbers. we know that this is true. This is obviously true in the real sense, that is when a comma b belongs to R, the real numbers, we obviously know this is right, but we have to check and verify whether this is true in a complex analysis. So, let us see how we can do this. Okay. Now, fix a particular a belongs to the set of all complex numbers. Okay. Then let a new function g of z is defined, which is equal to e raised to z into e raised to a minus z. Note that this fixing of a is actually arbitrary. You can choose any a in the complex number, and here we are defining a new function with respect to z. Okay. Now let us see what is g dash of z. Okay. G dash of z is equal to, we can use the UV rule here when we are using the differentiation. Note that in complex analysis also UV the whole dash is equal to U dash V plus UV dash. This is true also in the complex analysis case. Okay. So, I am going to take d by dz of e raised to z into e raised to a minus z plus e raised to z into d by dz of e raised to a minus z. Okay. We are taking derivative with respect to z. So, we already saw that d by dz of e raised to z is e raised to z, and e raised to a minus z is remaining like that, plus e raised to z into, what happens here is e raised to a minus z, the derivative will be e raised to a minus z into the derivative of a minus z with respect to z, that will be minus 1. So, we are getting it to be e raised to z into e raised to a minus z minus e raised to z into e raised to a minus z. So, it cancels out and we are getting 0. Okay. Now, you got something like this. We obtained g dash of z is equal to 0. Okay. So, when g dash of z is equal to 0, and note that z is an arbitrary complex number in C. That is, we are getting from here g dash of z is equal to 0 for every z belongs to C. This is something which we had seen in preposition 2.10. Please refer preposition 2.10, and from this preposition we are going to get that, yes, g of z is nothing but a constant function. So, since it is a constant function and I am introducing the constant w, and I am saying that g of z is equal to w, say. I am choosing the constant to be w for every, it happens for every set belongs to C. Okay. Now, we have e raised to z is equal to, yes, 1 by just expanding and writing, I am getting 1 plus z by 1 factorial plus set square by 2 factorial plus set cube by 3 factorial plus etc. right. So, that means e raised to 0 is equal to 1, right? E raised to 0 is equal to 1. Okay. Now think about g of 0. Okay. What is g of 0? G of 0. G of 0, earlier we had defined g of z is equal to e raised to z into e raised to a minus z, right? Defined so. We had defined so. Okay. So, instead of this z, I am going to take 0. So, I am going to get e raised to 0 into e raised to a minus 0. Fine. So, e raised to 0 we now got as 1. So, that is nothing but 1 into e raised to a. Fine. That is equal to e raised to a. Fine. But we already know that this g of z is a constant. That means g at 0 will also be the constant w. So, what we obtain now is g of 0 is equal to e raised to a, which is equal to w, right? So, let us see what happens then. E raised to z into e raised to a minus z. What is this? This is nothing but g of z. It is defined so. And we are saying that that is equal to the constant w for every z belongs to C. And but now we just saw that g of 0 is equal to w, that is equal to e raised to a, right? So, this e raised to a can be substituted here in the equality. So, I am writing this is equal to e raised to a, right? This happens for every set belongs to C. So, what did we now obtain? We now obtained that e raised to z into e raised to a minus z is equal to e raised to a for every set belongs to C, right. So, now let us see what all things we are going to get. Okay. Here note that z is an arbitrary complex number. First of all, and also we can fix the a we fixed earlier as we like, that is also an arbitrary number. That means the z and a minus z sitting here, z and a minus z, they are arbitrary complex numbers. Fine. So, what can we conclude? We can conclude that e raised to, here what it, you can say that e raised to a is nothing but, just for your information, we got this right, e raised to z into e raised to a minus z is equal to e raised to a, right. But this e raised to a is nothing but e raised to z plus a minus z, right. So, we are getting a kind of intuitive feeling that, or we proved that e raised to z into e raised to a minus z is equal to e raised to the sum of the powers. So, that is what we had claimed and that is what we wanted to prove. So, what we now got is e raised to a into e raised to b is nothing but e raised to a plus b for every complex number a and b, right. So, what did we prove? We proved the same property that was for this exponential function in the real sense, also in the complex scenario. This is the property which is satisfied by the real exponential function. We now prove that the same property is satisfied by our complex exponential function, which is a good behavior, right? Now, so e raised to z into e raised to minus z, what can be done? We can say that this is equal to e raised to z plus minus z, which is equal to e raised to 0, which is equal to e raised to 0. We had seen that it is 1, right? So, from this what can we conclude? We are saying that this is one complex number, right? E raised to z. E raised to minus z is also a complex number. When we are multiplying both the complex numbers, e raised to z and e raised to minus z, we are getting 1. That will definitely imply e raised to z can never be 0, because if it is 0, when we are taking the product, we will never get 1, right? So, it is never 0. So, what we are going to get there? We got this e raised to z for any complex number z can never be 0. So, this is another property we are going to get in complex analysis class also with respect to the exponential function here, and this is obviously true in the real sense. Okay. And also from this we are going to get something else. We know that now e raised to z into e raised to minus z is equal to 1, right? That will imply e raised to minus z is nothing but 1 by e raised to z. This is always true for every real number z, but we are saying that this is also true for every complex number z. So, that is again in turn a property which we are going to get as the same behavior of the exponential function in complex analysis classes also. Okay. Next, let us see what we are going to see. Fine. We have exponential function of z bar. Okay, that is nothing but, yes, we can represent it as exp of z or e raised to z. So, instead of z I am having z bar, suppose it is so. What is this equal to? It is equal to the power series n is equal to 0 to infinity. Instead of z I am having z bar, the whole raised to n by n factorial, right? This is equal to summation n is equal to 0 to infinity z raised to n by n factorial, the power series, the whole bar, right? Because conjugate, if we are having sum of two complex numbers, the whole conjugate, that is equal to the respective conjugates to be added together. Just to rewind, we can write here, because z1 plus z2, the whole bar is nothing but z1 bar plus z2 bar. That is the property of conjugates. Okay. So, I can use that here, and that is nothing but, what is this? This is nothing but the exponential function, yes, e raised to z, the whole bar, right? Or in the other representation, exp of z, exp of z, the whole bar, right? So, that is something which we now got, which is a nice property of exponential function. E raised to z bar is equal to e raised to z, the whole bar, a nice property of exponential function. Okay. Now, suppose if, let's see what all properties we can end up with. Suppose if theta is a real number. Okay. We already have modulus of z square is equal to z bar. We define the modulus function like this. When we are coming up across the complex numbers for the first time, we define it like this. So, suppose if theta is a real number, think about the following: e raised to I theta. Okay, that is definitely a complex number. Okay, and think about the modulus square. Fine. So, definitely by using the property of the modulus or the definition of the modulus function, I am going to get e raised to I theta into e raised to I theta the whole bar. Fine. That is equal to e raised to I theta into, we know this, right, e raised to I theta the whole bar is equal to e raised to I theta bar. So, I can write like this, e raised to I theta bar. E raised to, what is the conjugate of I theta? That will be minus I theta. E raised to I theta into e raised to minus I theta. We had already proved that e raised to a plus b is equal to e raised to a into e raised to b is equal to e raised to a plus b for every a comma b belongs to c. So, this is equal to e raised to I theta minus I theta, which is equal to e raised to 0. We had already proved that e raised to 0 is equal to 1. So, what did we just prove? We proved that e raised to I theta the whole square is equal to 1. This is also a definite nice property. The whole square is equal to 1, that will mean modulus is equal to 1. So, that is we can write for every real number theta, right. Okay. Nice property of e raised to z. Now, what can we now further get? Now, generally modulus of e raised to z the whole square is equal to e raised to z into e raised to z the whole bar, right. That is equal to e raised to z into e raised to z bar. Fine. That is equal to e raised to z plus z bar. Very much fine. So, some small properties which we learned earlier. If z is equal to x plus iy, we have z bar is equal to x minus iy. So, z plus z bar is equal to x plus iy plus x minus iy. That means iy and minus iy will cancel out and you are getting 2x, where x is the real part of z, right. Fine. And note that y is the imaginary part of z. So, what did we just obtain? We obtained this to be equal to e raised to twice real part of z, or to be better we can write like this, exp of 2 into real part of z. So, now we obtained a very important property. The property is modulus of e raised to z the whole square is equal to e raised to 2 into the real part of z, right. That is equal to e raised to real part of z the whole square, right. So, you are having a square here, a square here. So, removing the squares, we are going to get modulus of e raised to z is nothing but e raised to the real part of z, which is in turn a very important property we are getting here for exponential function. Now, thus we are concluding in this session that e raised to z has all the properties as that of the real function e raised to x. So, as of for now, we can stop here, and in the next session you are going to take inspiration from the real power series, and we will define trigonometric functions in complex analysis. So, thank you, and let's see in the next session.